Alright, let's make some magic internet money. Hey everybody, welcome back. My name is Jacob, and welcome to the second installment in this blockchain in Rust tutorial series. Of course, in this video, we're going to be going over mining and how to generate all those magic internet dollars. Sort of. We'll give it a little more concrete definition than that. But yeah, let's jump in. Before we actually start, there's just a couple things to note. You can install Rust, you can get Git, and the code is on GitHub at that link right there. All this will be in the description down below. And let's actually jump into the tutorial. So, mining. It's this kind of hazy concept that, you have like pickaxes and you're hacking away at magic codes and then all of a sudden, boom, you find bitcoins, right? Well, not exactly. Let's go back to something we discussed in the first video, and that is hashing, the concept of hashing. Essentially, so in this tutorial series, we're using the SHA-256 hash function. That's an algorithm that defines a series of steps you can perform on some bytes that will then generate this 32 byte long just string of bytes, and it's a unique reproducible fingerprint for whatever data you gave the algorithm, and that is important. You can't derive the data from the hash, but you always get the same hash from whatever data. So no matter how many times I run the SHA-256 function on this string, when you interpret it as just a series of bytes, GeekLaunch, you will always get this hash, A17D5, etc., etc., etc. And the same for this string, geek space launch, you'll always get 1D8E72. It goes on. And you'll notice that even though I just inserted a tiny little space here, innocuous little space, it changed the hash drastically. Like, there's hardly any similarity between these two, right? And that's an effect known as avalanching. So if I change a little bit of data, you cannot really predict a little piece of the data that you're hashing. You can't really predict what the changes are going to be to the hash unless you actually perform all of the steps of actually hashing the data. Now, this is, again, it's really important. So I decided I would have a little bit of fun with this and try and find a piece of data that when you hash it, it has the same 3 bytes. It starts with the same 3 bytes as the hash for geek space launch when you interpret it as bytes, right? So I found these 4 bytes in a row, 196, 201, 152, and 0. And I found that by brute force. I just tried combination after combination until I found one that did this. And the hash of these 4 bytes starts with the same 3 bytes as geek space launch does when it's hashed. And this actually took my computer, because I wrote a script that did this. Obviously, I didn't do this by hand. I wrote a script that did this. It took my computer 17 minutes and 44 seconds to calculate this. So, this is just matching the first 3 out of 32 bytes. Imagine how long it would take to match another, just one more byte, or even try and match all of them, trying to find a collision. A full 100% collision. That would be 2 distinct pieces of data that generate the exact same hash when you run that function on them. And that is super hard to do if you do it by brute force. And again, this is really important. It'll come up in just a bit in this video. So now let me introduce this concept called difficulty. Now it's called difficulty. It's the same deal. We're just going to implement it a little differently than most other cryptocurrencies do, but other cryptocurrencies, including Bitcoin, they call it difficulty, and it performs basically the exact same thing. Obviously, the implementation is just a little different. We're going to implement it in a little bit easier way. I think it's easier to understand this way. But you know that Bitcoin does pretty much the exact same thing. So here is a little more in detail what difficulty is going to look like. So when you hash a block with SHA-256, you get a 32 byte hash. Now, let's say we interpret that hash as a number, okay, and we're actually just going to take the first 16 most significant bytes and interpret those as a number. That would be a 128-bit number. If we do that and then come up with another number called difficulty. Now, difficulty will just be a number that we hard code in for now, and we'll just say, all right, difficulty is this, because this will affect how we mine things later on. Don't worry, this will become clear after we implement it and start using it. If you're confused right now, don't worry. So we'll have this number, we'll call it difficulty, and we'll compare it to the first 16, or the 16 most significant bytes of the hash of the block, and we'll interpret those 16 bytes, those most significant 16 bytes of the hash of the block, we'll interpret those as a number, and we'll compare it to the difficulty. Now, if the difficulty is greater than the 16 bytes of the hash, then we'll consider that a valid hash. Okay, there's a little more research you can do here if you so desire, but for now, let's go over to the code and implement it. And just one more note, quick note, little versus big endian. The most significant bytes are actually going to be at the end of the hash. If we interpret it as a number, that's due to something called endianness. It's just how the bytes are stored in memory, usually. So if we were to take an unsigned 32-bit integer, 42, its hexadecimal representation looks like this, right? We have the most significant digits here, there's zeros, and then a 2 and an A, right? So that's kind of similar to how a big endian computer would store the bytes. It would store 00, 00, 00, 2A, but a little endian, and this is actually more common, little endian, more common on actual like computers. Sometimes when you're doing networking stuff, you'll use big endian, but we'll ignore that for now. We're just going to use little endian. Little endian is more common on like computers, and it will reverse the order of just the bytes, not the bits, just the bytes. So instead of having 00000002A, which is kind of like how we humans like to read it, the computer likes to read it 2A 000000. Notice that it's not like A2 or some other weird combination if all the bits were flipped or something like that. It's just you're reversing the order of the bytes. So we'll be able to do this. It's no problem. In fact, I wrote a little function that'll help us. This just means that the 16 most significant bytes of the hash, if we interpret them as a number, are going to be in this range. It'll be 16 until, 31. And here are two links where you can look at this for yourself. Another note about this is when we print out a hash, that means that if we said, okay, it has to be less than this number or something, we set the difficulty to be kind of low. That means all the zeros, the low numbers, are going to be on the right side of the hash when we print it out, not the left side like we'd be used to. All right, but let's go over to the code and implement a check difficulty function. Okay, so this is the code exactly as it was left at the end of the first video, except I added one function, and you can get this from GitHub. It's this function, difficulty bytes as U128, as an unsigned 128-bit integer, and that'll take a vector of bytes, and all it does is it takes the last byte in the vector, well, we're assuming it's 32 long, and it shifts it over by 15, and 15 times 8, because that's how many bits you have to shift it over. And it adds them all. This is a single OR, is like it's a bitwise OR, so it's kind of like addition. It basically is addition in this case. And then it's all interpreted as unsigned 128-bit integer, and these are all in order, 31, 30, 29, 28, etc., etc., etc. I just wrote it for you because it's kind of a boring function to write on video. So we'll be able to use this, and actually it'll be really straightforward now to implement a check difficulty function. So I'm just going to actually add it here as just like a plain function, pub fn check difficulty, and that will just take a hash. So we'll say hash, it'll be reference to a block hash, and then it'll take a difficulty value, and that will be an unsigned 128-bit integer, and that will just return a boolean value, whether or not when you compare these, is the hash, or just those 16 most significant bytes, are those does it fit the difficulty? That's just the term I'm using. So this will actually be a single line. We're just going to say is difficulty greater than, and then we'll call this function difficulty bytes as u128. So difficulty bytes as u128, and we'll pass in this hash. And that's literally our entire check difficulty function. But I just really want to make sure that you understand what's going on here. We're converting the last 16 bytes. Remember, these are bytes. Last 16 bytes to an unsigned 128-bit integer, and then just doing a greater than comparison. So that's what's going on here. And now we can move on to the next step. So we're going to introduce this concept called a nonce, and it's a, well, okay, so we have our block, right? And we generate a hash, and it doesn't fit the difficulty that we've specified beforehand. Now what do we do? Because if we generate the hash again, we'll get the exact same series of bytes, because remember, it's unique to the data and it's reproducible, so you get the same thing every time. So we somehow have to change the bytes that we're hashing. But of course, I mean, eventually the idea with this project is to eventually add support for transactions, right? Just like a normal cryptocurrency. But we can't go on and just like change the transactions. That would violate all kinds of principles. So we totally can't do that. Instead, what we're going to do is introduce this field called a nonce, right? And so this nonce is arbitrary data. That's literally what it is. We can put whatever we want in there, change it at will, and the idea is eventually that will, you know, when we hash it all together, that will generate a hash that matches a difficulty. And so the nonce ends up being kind of like the key to this puzzle, where the puzzle is finding the hash that matches the difficulty, right? So this is what our mining strategy is going to look like. We'll generate a new nonce, we'll add it to our block, we'll hash all those bytes together, and then we'll check the hash against the difficulty. And if it doesn't pass the difficulty check, then we'll go back to the start, generate a new nonce, hash those bytes, check the hash against the difficulty. Does it pass? No. Okay, go back to the start, generate a new nonce, hash those bytes together, check the hash against the difficulty, and we'll do this until it matches the difficulty. And then we can add the block to our blockchain and submit to peers, etc., etc. But we don't even have a blockchain running yet. We've just been working with single blocks, and we don't have any networking. So we'll just kind of gloss over those steps for now. Right now, we're just caring about actually successfully mining a block. So let's implement that mining algorithm. So we'll come over here, and there's actually something I forgot to do when we did difficulty, and that is actually we're going to have difficulty be a field of our block struct. So I'm going to add that here, difficulty, and that is an unsigned 128-bit integer. And we'll add that here, difficulty, whoops, difficulty, unsigned 128-bit integer. Beautiful. Okay, and then we have to add that to our bytes here when we hash stuff. difficulty. Wonderful. So now let's add a function to our blocks, our block implementation block here, called pub fn mine. Okay, and that will take a mutable reference to ourself, and then it'll just do everything for us. Okay, it'll be a pretty simple function actually. So we're going to say for nonce attempt in one will go from 0 until so our nonce is a 64-bit unsigned integer, and we'll just go there until there dot max value. All right, so now we're just going to loop through literally every single unsigned 64-bit integer value until we find one. So we'll do this. We'll say self.nonce equals nonce attempt. We'll say let hash equals self.hash. And then we'll check the hash to see if it matches the difficulty that we set up here in our block struct. So we'll say if check difficulty, and then we pass in the hash and the difficulty. So if check difficulty, here we are. So we'll pass in the hash and then the difficulty, self.difficulty. So if that returns true, then we know that that hash fits our difficulty. Then we'll just say self.hash equals hash and return. And that's literally our entire mining function. As you can see though, if this fails over and over and over again, this will get it'll take a long time, because this hash function right here is going to be really computationally expensive. Okay, so this can take a really long time. And so let's go over here and try it out. We can delete all this code. We don't need this. This is from the first video, and we're experts at that now. Just kidding. Let's actually keep this and just insert a difficulty value here. Now remember, this is something that the first 16 bytes have to be less than. So I'm going to insert zeros, okay, 16 bytes worth of zeros, like so. Now, this would be actually a very, very impossible difficulty, because no unsigned integer is less than 0. So what we actually want to do is probably change all of these to F, which is 15, because this is hexadecimal. And then all this means is that the most significant byte, single byte of our hash has to be 0 in order for this block to be considered mined. So here we go. I'm going to add one more thing here. Block.hash will block hash like this. Okay, so this will print out the block before we've mined it, and then we'll say block.mine, and let's print it out again. And then we can say cargo run and see what happens. It shouldn't take very long. Okay, and we got two different hashes here, but we actually can't see the nonce. So I'm going to move back over here, and we'll add that to our printout here. We'll say nonce, and then print out the nonce, like so. All right, let's come back over here and run it, see what happens. All right, and so we get nonce 260. All right, beautiful. Let's make it a little bit more difficult and replace that with a 0. So this means that, oh, by the way, you can see these 2 bytes, or this 1 byte, it's 1 byte, is 0. And now this is actually going, because we'll flip the order of the bytes. So you'll see here, if we run it, now we have a 0 and 5 and 0, 0. And you can see our nonce is a little bit higher than 260, 1,577. So let's make it a little bit harder. We'll change that to an 8. And now I'm going to time it. So we'll time cargo run and see how long it takes. So just about a second. Of course, that includes building it, compiling it, whatever. And we get 3,091. Of course, if we were to run this again, we get the exact same thing, 3,091. Let's make it a little more difficult yet. Oh, it's taken a while. It's taken a while. You might be able to hear my computer start to spin up. Who knows? Will this even complete? It might take it a long time to find a... Oh, there, 14 seconds. And we got 118,318. So let's, if we were to kind of cheat, we could try setting the nonce, I think this one's the nonce, to that number, 118,318. Or, yep, okay. And now, if we just comment out these guys, we should get this exact same hash. And sure enough, it ends with those 4 zeros. So now we kind of have to review, what does this nonce actually mean? Because if we were all in a network and this was a cryptocurrency, what would it mean for me to tell you that this is a nonce that fulfills this difficulty? Well, if you think about it, that means that I have performed this work. That means I have spent these 14 seconds generating that nonce. And that is important because you can set a difficulty such that if everyone on your cryptocurrency's network is hashing all together, you can say, all right, I'm going to adjust the difficulty such that such that it takes, even with everyone working together, it's going to take them about 10 minutes. And that's what Bitcoin does. It says, all right, this is how much hash power is on my network. I'm going to set the difficulty so it takes about 10 minutes for everyone all together to find a nonce that cracks, that mines. It's the key to, it solves the next block. And this is important because then if someone else wanted to fabricate a block and solve it faster than everyone else, and then distribute their fabricated block somewhere, that would mean they have to have it. They would have to have more power than the rest of the network combined. So they would have to make up over half of the hash power on average, in order to reliably carry out such an attack. You know, substituting in fake blocks or blocks that they've mined, that where they have only allowed certain transactions, certain pieces of information to be part of this payload. But if you set the difficulty to be difficult enough, then it would be very difficult. That's why it's called difficulty. It'd be very hard for an attacker to hash and find the nonce faster, reliably, than everyone else on the network. They would just have to be really lucky over and over and over again, or invest a ton of money in hash power. And that's part of what makes the decentralization of things like Bitcoin such a strong feature. But anyways, I've been going on for a little while, and that is the end of what I have for you in this video. So I hope you enjoyed it. I hope you learned something, and I hope you come back for the next one, because eventually we're going to be getting to transactions and blockchain verification and smart contracts, and I'm really excited to show you guys all about that stuff. So until then, my name is Jacob, and have a good one.